All right. Hi, everyone. Welcome to VSPG. Today we have Lukáš Ackerma. He's presenting about black shales as geochemical markers of paleoenvironmental changes in tectonic setting along active continental margins. Lukáš is a research scientist at the Institute of Geology of the Czech Academy of Sciences in the Czech Republic, where he leads projects in isotope geochemistry, and he is also a part-time researcher at the Czech Geological Survey. His work uses elemental and isotope geochemistry to investigate the petrogenesis and evolution of sedimentary and igneous rocks, with the goal of constructing the evolution of Earth's mantle, crust, and oceans through time. In particular, he focuses on trace element and stable isotope systems of molybdenum, iron, and silicon as proxies for the extent of oceanic and atmospheric oxygenation during the Precambrian, especially across the Neoproterozoic to Cambrian transition. Thanks so much, Lukáš, for presenting for us today. Take it away.
All right, thank you very much, Alex, for the introduction. So, hello everybody. So today I would like to share you some of the data we get for the black shales. So we had a couple of projects a while ago, maybe 2 or 3 years ago, and we focus on the phenomenon whether the black shales can serve as geochemical markers of paleoenvironmental changes and tectonic settings, and we focus especially on the active continental margins because we realize that there's some kind of the significant gap in the amount of the data obtained for this kind of the rocks. So just a quick summary: what are the black shales? Of course, we all know this is the fine-grained laminated sedimentary rocks. And these are typically organic rich, so they are rich in the organic matter, in other words, on TOC, so total organic carbon. So this is a couple of, there's several people make some kind of this different discrimination of the black shales and the normal shales, but let's say, that we can assume that if the shale contain more than 0.5 white% of TOC, we could call it the black shale. So the black shale typically form quite large horizons of the sedimentary rocks in different package of the sedimentary units. And these are excellent markers of slow sedimentation and low oxygen environment because they are essentially reducing rocks. So they are depositing in reducing condition with a low oxygen contents. And they are really intriguing archives because they have been present since Archean to the recent time and are very commonly enriched in the autogenic metals. So that means that they are rich in the metals which are directly precipitating from the seawater. So that means that they can serve as a markers of changes in the seawater chemistry. So they represent a beautiful archive of oceanic and environmental history. So we can trace to the past, the oceanic and environmental history of different systems. So as I said, we focus on the active continental margins because there are a number of studies dealing with the black shales, especially in the recent conditions, like the black shale deposited in the Black Sea or the Cariaco Basin in the Caribbean, or even the black shales on the western side of the United States and the California margin. But if you are looking back to the past, the data from the active continental margins are much less abundant. So we think that one of the best archive to look on it are the accretionary complexes. So this is the complexes of the sedimentary rocks developed above the subduction zone, because in accretionary complexes you can commonly found the remnants or even the wall packages of the succession. We are calling it oceanic plate stratigraphy. So the OPS basically record the geological history of the plate from its birth in the middle ocean ridge to its death in the subduction zone. So it's the composition strongly depends, of course, on how far we are from the arc or from the continental or oceanic plate and from the subduction zone. So as we are closer to the arc or to the continental, the oceanic crust, we can see the increasing proportion of the oceanic sediments. So this is some kind of idealized profile of the ocean plate stratigraphy, which refers to the lower plate successions that are composed by the middle ocean ridge basalts at the base. And then during the Phanerozoic, there's quite a different thickness of the package of the bedded shirt. So this is the biogenic sediments, the deposition of the silica-secreted remnants of the silica-secreted organisms, right, like the radiolaria and so on. And then on top of it, there's a different proportion of the shale of the mudstone. So basically the hemipelagic sediments, shales, mudstones, black shales, or even the siltstones. And altogether, this kind of package represents the lower plate. And of course, if the oceanic plate travels along the plume or through the plume, so then they have also the members of the ocean island basalts or carbonate, a couple of the carbonates capping the oceanic island basalts like the corals or something like that. Whereas on the upper plate is completely different story. This is the sedimentary rocks derived directly from the arc or from the continental crust itself. So this is now mostly represented by the sandstones and the conglomerates, altogether forming some kind of turbidite currents, and which are deposited directly in the trench. So that means that the most of the rocks itself in the oceanic plate stratigraphy is mostly derived from the upper plate, but we can also recognize the members of the ocean plate stratigraphy from the lower plate, which is the most important thing, because this is the record of the sedimentary unit deposited on the lower oceanic plate. So basically, the research objectives of our study was to gather some new information on black shales that were deposited in different active margin settings. So we were looking on 3 different settings. The first one was represented by directly the volcanic arc. The second was related to the seafloor, so the deposition of the black shale direct on the seafloor in a close relationships to the mid-ocean ridge basalts or the hydrothermal processes. And the third one was the conditions, occurring directly in the trench, so in the accretional wedge itself on the trench slope. So the black shale is deposited over there. So we try to identify the exact mechanism, the primary mechanism and conditions that leaded to the deposition of the black shale. So what were the conditions, the depositional conditions of the black shales? What were the potential links to variable tectonic processes? So the formation, the birth and the death of the volcanic arc, and the spreading on the seafloor closer to the subduction zone in the accretional wedge, and then the condition in the accretional wedge itself in terms of the third tectonic settings. So altogether, all these pieces of the information, we think that they can expand our understanding of paleoenvironmental changes in seawater composition and deep ocean atmospheric oxygenation, because we looked at the Neoproterozoic Cambrian transition. We studied the accretional wedge, which was developed during the Neoproterozoic Cambrian transition, which was, of course, we all know that is the marked changes in the paleoenvironmental condition, large increase in the oxygen in the atmosphere, and of course the huge relationship to the Cambrian explosion of life. So to do so, we focus on the Abelian-Cadmian belt, which is really more than 5,000 kilometer long evolutionary belt, consisting of many microcontinents developed along the northern margin of Gondwana. So this belt was developed between, let's say, 670 to 550. So basically, it late Neoproterozoic, but some of the parts also developed in the early Cambrian and the late Cambrian. I'm sorry. So this is the basically active margin settings, and the different microplates can be distinguished, can be separated to two principal groups. One is the Avalonian belt or Avalonian remnants. So this is the remnants we can understand that we can see right now in the Newfoundland, in Canada, or New Scotia. But on the other hand, in Europe, on the European side, right now, there are some Cambrian remnants like the Ossa Morena in Spain, Armorican Massif in northern France, but also the Tepla-Barandian unit. So the Tepla-Barandian unit is one of the microplate involved in Avalonian belt. And the Tepla-Barandian unit right now is exposed directly in the center of the Bohemian Massif. So this is the present situation from Western Europe, Spain, Portugal, France, Germany to the Czech Republic. There are several exposures on the Varscan belt. So this is completely different story. Varscan belt represent the continental collision remnants, remnants related to the continental collision during the late Paleozoic. But within these remnants, by the brown color, there are some Cadmian relics like the Tepla-Barandian zone. So we focus on the Tepla-Barandian zone in the Czech Republic, which is quite extensive part of the Cadmian remnant. So this is basically the basic and very simplified geological map of the Tepla-Barandian zone, which is almost fully occupied by the Blovice accretional wedge. So the accretional wedge developed in about 60 million years from, let's say, late Neoproterozoic to early Cambrian. So it basically consists two different units. On the eastern side, so with this violet color is a double volcanic complex. So this is the volcanic arc itself. And from the western side of the site, this is quite extensive accretional wedge. So this is a 5 kilometers. So this is really extensive accretional wedge, which is composed by two different units, the belt 1, 2, and 3 with Arabic numbers. So these one all, which contain the blue patches, are the basalt-bearing melanges. So this is a different basaltic blocks embedded in the siliciclastic succession. So this is a part of the disrupted ocean plate stratigraphy. The most of the basalts are mid-ocean ridge basalts, lithologies, but there are also a number of basalts which belong to the ocean island basalt. So that means that the seamounts were also involved in the subduction. And in comparison, there is also the coherent trench-filled turbidites representing the sediments from the upper plate. So this is the belt 1, 2, and 3 by the Roman numbers, which are almost completely devoid of the basalts. So we have two different principal units of the accretional wedge. And within the accretional wedge and within the volcanic arc itself, there are three different tectonic settings that contains the black shales. So the tectonic setting 1 is represented by black shale that directly overlies a volcanic arc, whereas the tectonic setting 2 is represented by the black shales, which were directly deposited on the seafloor in close association with middle ocean ridge basalt magmatism and associated hydrothermal evolution. And finally, the tectonic setting 3 is represented by the black shales, which were deposited directly in the accretional wedge in association with trench-filled turbidites, no basalts, no hydrothermal evolution related to the magmatic processes within either on the oceanic plate or volcanic arc. So this is our three different tectonic settings, which are really well developed and can be really nicely sampled in the field within the accretional wedge in the Tepla-Barandian zone in the Czech Republic. So let's first, take a look on the setting 1, so the arc-related black shales. As I already said, so this is the horizon on the black shale, which is a thickness of about 50 to 200 meters, which can be really nicely mapped and sampled in the field. They occur in a really nice stratigraphic position. So the volcanic complex or the volcanic arc itself is represented by quite a thick package of the rhyolites, basalts, and the andesite lava flows. And directly on the uppermost rhyolite tuffs, the black shales are deposited. And then they are passing to the siliciclastic turbidite succession of the Štěchovice group, which is also very, very thick. So one of the most important thing, it's quite striking for us that the black shales of this kind of the settings are really, they have large lateral extent. So you can trace them, for the tens of the kilometers, and they occur in a quite similar thickness over the volcanic arc itself. Unfortunately, we were not able to date them immediately, exactly, because we are not able to extract some of the zircons from it. But we dated the upper portion of the whole portion of the siliciclastic turbidite succession as well as the relative tuffs. So from the ages from these two lithologies, we can estimate the age of the deposition of these black shales between 580 and 560. So this is, we are speaking about the late Ediacaran era, so the latest Neoproterozoic era. So as I said, this is some kind of a really nice and well-developed stratigraphic profile. So we did some sampling and did collected lots of the geochemical data. So I'm going to present just a few of them. So altogether, along the sample section, which was about 800 meters long, coming from a double volcanic complex, so from the volcanic arc itself to the uppermost siliciclastic succession, we can see some kind of the variation in the major and the trace elements. For example, there is an increase in the silica content and a decrease of the magnesium and the lithium and the scandium contents closer to the arc. So that means, the silica increase because of the silicification, which is related to the magmatic history of the arc itself. And the lower contents of lithium and the scandium can be best interpreted as the decreasing amount, or on the other hand, increasing amount of the terrigenous material input, to the upper section of the Lečice member black shales. So for us, for the evolution was the most important thing was especially evolution of the TOC values. So the total organic carbon. Again, the closer we are to the double volcanic complex, to the volcanic arc, we can see the higher contents of the TOC and also higher concentrations of some redox sensitive elements like the uranium, molybdenum, and something like that. Whereas we are going to the upper portion, there are decreasing concentration all of these elements. So we suggest, or we think, that this is some kind of a record of the temporal variation in the seawater chemistry, but also the record of variable input of detrital material into the basin. So basically, the black shales were deposited in two different stages. The first stage, the stage 1, is marked by weakly anoxic condition with only low terrigenous input. And this is evidenced, for example, by higher TOC contents, higher molybdenum and uranium contents, and other redox-sensitive elements like chromium or something like that. And then the subsequent stage 2 is marked by the abrupt shift to oxygenatic environmental. So there is a shift from the anoxic conditions to the suboxic condition, which is somehow related to the increased amount or increased flux of the terrigenous material to the basin. So this is also very nicely expressed here in the diagram, a binary diagram, where on the x-axis is the enrichment factor of uranium, and the molybdenum enrichment factor is on the y-axis. So we can see that the decrease in the both concentrations from anoxic conditions from stage 1 to the stage 3. But in both stages, stage 1 and stage 2, we can see from the sulfur concentrations and from the sulfur isotopic composition that it was quite an unrestricted sulfide reduction. And then finally, the situation changed with the deposition of the flysch sedimentation, the flysch sediments during the stage 3. So the deposition of the turbidites from the overlying arc, so from the upper plate material, that occurred in a suboxic conditions, and these were dominated by vast terrigenous input into the basin. So altogether, we try to interpret of the data, why we can see the changes in the condition in terms of the terrigenous material flux and the changing of the condition from reducing to the oxygenated. And then we realized, that the age of the deposition of these black shales are somehow related to the global glaciation cycles, which occurred, during the late Archean. So we think that in stage 1, it can be related to the global sea level rise and the waning volcanic arc activity. So this is a deepening of the basin, weaker anoxic condition, and then later on during the stage 2, because of the global sea level fall related to the glaciation, there is an enhanced terrigenous supply from the waning volcanic arc, but the condition changed to the more oxygenated condition because of the decreasing or the sea level fall. And the stage 3 in the late Archean is completely connected with the compressional arc uplift and the restricted basin circulation. And it was a vast supply of terrigenous material to the basin because of the elevated inactive arc supplied material. So this is our story for the volcanic arc black shale. So we find out that this can be somehow related to global eustatic levels of the seawater. So in terms of the setting 2, this is completely different setting. Fortunately, there are not so many outcrops in general, but we are quite lucky that we can study 2 boreholes, which are quite big. So borehole A, Hromice, and the B, you can see there's all of these black horizon as a black shales itself. And we can distinguish the 2 different black shale types. One are the so-called normal black shales, which are rather low, in a low concentration of the TOC and the sulfur contents, let's say up to 5% of the sulfur in terms of the Hromice, and the same is thing for the Kamenets. And all of these, green and red colors are the black shales that are related to the volcaniclastic succession in terms of the Hromice, or even to the metal basalt layers in case of the Kamenets. So these are metal-rich black shales, so they are characterized by a really high concentration of vanadium, chromium, molybdenum, hundreds and thousands of the ppm, and they also contain very high concentration of the organic carbon and the sulfur. So this kind of the shales, they form decimeter to meter scale horizons. And these horizons are intimately associated with basaltic rocks, so with the hydrothermal input and with the magmatic history. So the previous studies suggest that the normal black shales originate in a semi-isolated basin with longer renewal times, whereas the metal-rich black shales, they form in the ventilated conditions with better access to the open ocean. But on the other hand, whether it was really substantial hydrothermal flux that caused high enrichment in many metals. So altogether, we try to focus on different things. We focus on the copper, zinc, and the osmium systematics. And we realize immediately that there's 3 different end members: detrital, autogenic, and hydrothermal metal sources, interplayed in the origin of the black shales. So in terms, for example, the zinc, more zinc and the lower aluminum to zinc ratio, that means that there is an increase of the autogenic concentration of the zinc. On the other hand, if you take a look on some of the normal black shales, the black circles, there is an increasing amount of the terrigenous material into the basin and the lower amounts of the autogenic metals. In comparison, the hydrothermal flux can be the best traced through the osmium concentration and the osmium isotopic systematics. The higher osmium concentration that are coupled with the lowering of the delta 56 iron isotopic variation is strongly connected with the hydrothermal flux into the basin. So speaking about copper and the zinc, oceanic mass balance cycles. So this is just some really brief introduction to these, two isotopic systems. So in general, there is only a limited fractionation for the upper crustal materials, but on the other hand, there's a vast geochemical modification of the both isotopic systems because of the organic complexation, clay absorption, or biological uptake. So in general, this is the recent cycles of the copper. So the most important input is the input through the rivers that delivers isotopically heavy copper. So let's say 0.7 in per mil, whereas the hydrothermal input and the input from the oil and dust are rather limited. And the same is true for the zinc. So the rivers, again, are the most important inputs to the basin. Hydrothermal and oil and dust inputs are rather minor. In general, the ocean is quite isotopically heavy in terms of the copper, let's say 0.9. In terms of the zinc, it's 0.5. So it's also isotopically heavier than the inputs, so than the rivers. So what about the outputs, the sinks of the copper and the zinc? So we are pretty confident that the oxic sediments like the manganese crust, oxygen manganese deposits, they are really important zinc and copper outputs. So in the blue colors, this is in the magnitude of the flux, magnitude of the input and the output of the copper and the zinc. So the oxic sediments are really important sink of the light copper and the light zinc. But we are still not sure about the margin sediments like our black shales deposited on the continental margin and the eustatic sediments. So that's why we focus on the copper and the zinc in our black shale horizons. So we can take a look on the data. The red color are the metal-rich shales. The black circles are again the normal shales. So we can see that the normal shales in terms of the copper isotopic composition, delta 65 copper, they are much, much lighter, and there is a beautiful variation with the copper. So they are going down even to -1, which is far much lower compared to the deep ocean, which is much more heavier, let's say 0.7 per mil, and even heavier to the bulk silicate earth. And the same is true for the zinc, which is not so well visible, but still, the most of the values collected for the normal black shales are much lighter than the values found in the deep ocean, for the recent deep ocean. So this is the data for the normal shales. For the metal-rich shales, unfortunately, the signal is not so well visible. So mostly, some of the data points are quite similar to normal black shales, whereas some of the data points, they are much more heavier in terms of the copper and the zinc composition. So what does it mean, in general? So we can see that the both values, delta 65 copper and delta 66 zinc, are lower than the recent dissolved ocean. So we suggest that the organic rich continental margin sediments with increased terrigenous flux, which is expressed, for example, over here. So this is a two different mixing lines with possibly two different end members for the normal black shales. And these represent the important sink of the isotopically light copper and isotopically light zinc. Whereas the metal-rich black shales, this is completely different story. They are typically much more heavier in terms of the copper, and there is a strong autogenic enrichment in the copper and zinc, which are mostly related to the autogenic enrichment itself, because usually the hydrothermal flux of these two elements is rather low. So what are the implications for the composition of the Neoproterozoic seawater? The Chifru and other studies have shown, that during the late Archean and the paleoproterozoic, there is an increase in the delta 65 copper in the black shales, and it was somehow interpreted to be related to the great oxidation event. So that means that there is more and more delivery of the oxidative of the heavy copper into the ocean because of the oxidative weathering of the crust. And since that, the values is about 0.2 per mil. So that's exactly almost the the Bohemia metal-rich black shales has about 0.6 most of the values. So it's quite similar to the modern deep ocean value in terms of the copper, and this is similar for the deep ocean value of the delta 66 zinc. So that means that even in the late Neoproterozoic, the values are a little bit higher comparing to the paleoproterozoic era. So that suggests high level of surface oxygenation since the Neoproterozoic and Cambrian transition. And in terms of the zinc, it also means that there was a well-balanced cycle of phosphates, because the zinc is a closely related to the phosphate cycle in the Neoproterozoic. So let's just have a quick summarize of the osmium isotopic systematics. Of course, this is a completely different story. Rhenium and the osmium is both metals are strongly bound to the organic matter. So that means that in normal black shales, the autogenic rhenium and the osmium dominates. So that means that the most of the budget is dominated to be derived from the organic matter itself. Whereas the metal-rich black shales, as I already showed you, this is a large hydrothermal contribution of osmium. And also, we realize that the osmium 187, 188 ratios are much more radiogenic, comparing to the common hydrothermal fluids in the ocean. They are rather maybe related to the subduction-related fluids. So unfortunately, the rhenium osmium systematics of the black shales from the setting 2 is quite perturbated. You can see over here that most of the data points are somehow dispersed around the reference line, but they are not well-defined isochron. So this is some kind of the probably effect of the higher terragonous flux. But anyway, if we just try to recalculate all of the data and get some kind of what should be the value of 187 to 188 ratio of the osmium of the black shales, of the autogenic portion of the black shale in the Bohemian Massif, black shales of the Neoproterozoic era, we will get the value of the 0.6. And Tripathi and Sinks in 2015, they published one paper in the Chemical Geology that they show really nice profile from the late Archean to present, and they suggest that there was a significant increase in value of a 187, 188 ratio, especially in the late Neoproterozoic. And they interpreted it that there was a huge influx of oxidized crustal material into the ocean during late Neoproterozoic. But this is, not something, we cannot confirm from our data, because our value of 0.6 is much lower than the value, which is, value for the present day seawater, and also the value of the seawater, what was predicted if it was a rapid influx of oxidized crusted material. So it seems, that the ocean at that time was not fully oxidized, and it was not some significant increase as suggested by previous studies in terms of the osmium isotopic compositions. So the last setting, setting 3, we focus on the train slope black shales. So this is completely different story. We already moved to Cambrian era. So from all of the ages we obtained for the surrounding gravities and for the siltstone, we think that we estimate the age of the black shale deposition to 510 to from 530 to 510. So we are in the late Cambrian, in the early Cambrian. So the black shales itself form quite a thick horizon. So this is the blue color inside. How does it look like from the field map? Fortunately, there is an edit inside and open pit. So we can again do the sampling along the stratigraphic interval from the lower beds, which are represented by the bedded siltstones and the shales, through the unit 2, which is represented by the black shales itself, to the uppermost unit 1, which is again the bedded gravicky. So this is a mostly oxygenated environment, and then there is a layer of the black shell inside, which must indicate marked change in the deposition condition to some reducing ones. So the deposition occurred rather in a short time span. Unfortunately, there's also some pronounced silicification inside, which is obviously late stage. So we did some kind of elemental profiles along the stratigraphy. So we can see in the base of the unit and the gravities and the shales, a very low TOC concentration, so very low concentration of the organic carbon, of the sulfur, and also some redox sensitive elements. But then, in the transition to unit 2, which is basically the black shales, then we can see a very steep increase in the TOC values, almost up to 7%, and the sulfur again is also going up to almost 4%. And there is some kind of decrease along the unit, along the upper portion, along the stratigraphy. There is a decrease of the values of the TOC and the redox sensitive element or something like that. So we interpreted this that the black shales at the base were deposited in eustatic conditions because there are very high carbon values, TOC values, and they became suboxic conditions toward the top of the unit 2, so it's over here. So just to summarize, there is a huge autogenic enrichment of the black shales in some redox sensitive elements like the molybdenum and the uranium. And also because of the high sulfur concentrations, we can also observe really nice thin depositional pyrite, which is mostly presented by some rhomboidal pyrite grains. So we did some laser ablation analysis and analyzed the trace elements and realized that all of these primary pyrites are very rich in the redox sensitive elements like the nickel, like the chromium, molybdenum, selenium, and something like that. And all of these autogenic metals are somehow related to the TOC values, like over here, correlation with the TOC and the molybdenum, and a similar pattern to the condition, which are related to the basinal restriction, the conditions we have right now, for example, in the Black Sea. And it's almost obvious that the redox sensitive elements are closely related to the precipitation of the sulfides in the euxenic conditions. So if the euxenic black shales record at least the local seawater composition, that means that our measured average value, the delta 98 molybdenum, which is somehow refer to the value of the extent of the euxenic condition of 1.2 per mil, it's much lower than the value we can see right today for the oxygenated ocean, which is 2.5. So that means that even in the Cambrian, we are already in the Cambrian era, which it's commonly suggested that it was a great oxidation. Of some of the studies, suggested that almost all of the oceans became fully oxygenated to the deep. So from our data, it doesn't look like. It rather argues against full deep ocean oxygenation, at least in the early Cambrian. On the other hand, if you take a look on the trace element systematics of the pyrites, because several studies of Cook et al., and many others, they suggest that the trace element systematic of thin sedimentary pyrite can be used to imply the level of the atmospheric O2 in the atmosphere, the levels of atmospheric O2 in the past. So following their calculations, their formulas, it seems, or our data would suggest, on the other hand, that the atmosphere was highly oxygenated. It contains about 27% of the oxygen. So that's some kind of the opposite to the molybdenum data, or to the trace element and the isotopic systematic directly coming from the black shales itself, because that would argue for the highly oxygenated early Cambrian atmosphere. So what I think some kind of the global implication or the lessons from the black shales we obtain for the continental margins. We think, or we suggest, that the arc-related black shales may be linked to the eustatic sea level changes, as well as dynamic arc topography, because not only the sea level changes play a very important role, but also the evolution of the underlying volcanic arc. So this is something we observe in our setting 1. The black shales at active arches with high heterogeneous flux may represent very important previously identified zinc of an isotopically light copper. For a zinc, it was suggested previously, but for the copper, it was still a big discussion on where is the main burial, the main sink of the light copper. So we suggest that the black shales, or in general, the organic rich sediments with high proportion of the terrigenous material inside, can be this kind of the sink. From our data, it seemed that the Archean Cambrian deep ocean remained largely ferruginous, so that means it was not fully oxygenated. There was no deep sea oxygenation, at least throughout all of the Archean and the Cambrian, which is quite not in agreement with many studies. Because of the formation of the trench slope, black shales is closely tied with the seismic and tectonic activity. We think that the formation of the trench black shales is closely related to co-seismic extension periods occurred directly in the accretional wedge. And finally, it seems from some of the data collected for the sedimentary pyrites for the Cambrian black shales that perhaps the early Cambrian atmosphere was really high in the oxygen. So it was maybe highly oxygenated despite the heterogeneous buried redox states recorded in the black shale horizons. So that's all from my side. Sorry, I was a little bit later. So this is just a brief acknowledgement. So I would like to express my gratitude to our black shale team, which is mostly based in the Czech Czech Academy of Sciences, but mostly, but also some colleagues from Charles University and the University of Alberta and the Czech Geological Survey. So thank you.
All right. Thanks, Lukáš. All right, let's open the floor for questions. You can raise your hand by finding the reactions button at the bottom of the screen. Click that and hit the raise hand button, or you can type your question in the chat and I can ask it for you. So I'll leave some time for people to come up with their questions.
Hi, Lukáš, maybe I start with a question. So just thinking about the osmium isotopes, do you think it's possible that you had a strong contribution of sort of hydrothermal activity that lowered osmium initial ratio and it doesn't represent global values? And following on it, if you have this restricted basin, to what degree it represents toxic conditions in deep ocean versus global ocean? I mean, in a restricted basin versus global ocean.
As well, where is it? Yeah, the normal black shales, we think that they are closely related to or the deposition was in a semi-isolated basin. So we think about the metal-rich black shales, which contain really high proportion of the osmium inside. So where is it? I'm sorry, it's over here. Yeah, it's over here. So all these red dots, it's really high osmium concentrations, Yeah, it's right, it's somehow related to the hydrothermal flux. But, this kind of the value we get, this is some kind of we try to extract all of the influence, coming from terrigenous material as well as the influence of the hydrothermal flux, But of course, there's always a big question if this kind of the value, let's say for our study 0.6, if it's value which can be rather connected with some kind of the semi-isolated basin, because we are pretty sure that there's definitely some kind of the connection with the open sea. But if there's a complete connection or if there is still some kind of restriction, it's always a matter of debate, So it's this is some kind of the speculation, of course, if this is a value which can express the value for the open sea, then it would argue against the full oxygenation or some kind of high influx of the oxidized crustal material, because in that case we should see much higher values which should be closer to the present day seawater water value, which is about 1.1.
So just following on it, this high enrichment in metals, to what degree do you think it reflects, again, hydrothermal process contribution versus global ocean?
Yeah, I think it's rather really related to the local conditions, because the global hydrothermal flux usually in the ocean, as far as we know, there are not so much data for hydrothermal fluids in general related to some magmatic and in general for volcanic activity in the oceans. But usually the fluids are rather unradiogenic, so usually they have 0.15, 0.2, 0.3. But our values suggest that this kind of values were much higher, let's say around 1. So that means probably rather local hydrothermal flux somehow related to the subduction related settings. So there's some kind of the input of radiogenic osmium throughout the subduction zones, as we can see, for example, for some mental lithologies or something like that. There's a strong increase of the radiogenic osmium in this kind of the subduction related settings. So we think it's somehow related to really local settings than the global. But this kind of the value is rather value for, as I said, it's for the shales which would have the least contribution from hydrothermal flux.
Thank you.
Okay, anybody else? All right.
So do you think this metalliferous black shales sort of, if I understand you correctly, might reflect metals sort of released through, I guess, subduction
Yep.
from the subducting plate?
Yeah, something like that. Some kind of definitely some kind of the influence from this with the subducting plate. Yeah, as in this kind of the stage, of the knowledge, we think that this is the most reasonable explanation for our data.
And it resulted in this hyper enrichment in metals.
Yeah.
Thank you.
Okay, then thanks, Lukáš. Sorry we don't have a bigger audience for you today.
Sure.
A lot of people are
I fully
coming
understand.
back from their conference, yeah. So, but thanks a bunch for this presentation, and thanks, Andre, for questions.
Thank you very much for the invitation, and maybe some of the guys they are going to see it on the YouTube channel if they will be interested.
Yeah, great. Okay, everyone, take care, and we'll see you in upcoming seminars.
All right. Thank you very much.
Thanks, Lukáš.
Thanks for the invitation. Thank you. Bye.